Hello, and welcome back to How It Really Works, where we disassemble the technology you use every day to understand the mechanics beneath the marketing. Today, we are tackling perhaps the most controversial button on your dashboard. It's the first thing many of you press when you start your car. It's the button with the A inside a circle and an arrow indicating off. We are talking about auto start-stop technology. If you listen to car forums, or perhaps your uncle at Thanksgiving, you've heard the definitive verdict on this feature. They say it is a gimmick designed purely to cheat EPA fuel mileage tests. They say it saves you perhaps $3 a year in gas, while causing $3,000 in damage to your starter and battery. They say the wear and tear of restarting an engine dozens of times on a single commute is tearing your bearings apart. It feels intuitive, doesn't it? We were taught for decades that starting the engine is the most stressful moment of its operation. So, voluntarily doing it at every single stop sign seems like mechanical suicide. But here is the uncomfortable truth. If you believe that, you are operating on outdated engineering knowledge. You are assuming that a 2024 starter motor is built the same way as a 1994 starter motor. You are assuming a hot restart is physically identical to a cold start. Both assumptions are wrong. Today, we are going to look past the annoyance of the engine shutting off and dive into the genuinely impressive engineering that makes it possible without destroying your car. We will look at the reinforced hardware, the battery chemistry, and the complex sensor fusion that decides when to kill the engine. And then, we will take this system into 3 real-world driving scenarios: the long red light, stop-and-go freeway traffic, and the drive-through lane, to see precisely what the costs and benefits are. Let's pop the hood on the mechanics of the pause. To understand why auto start-stop doesn't kill your car, we first need to understand what actually happens during a traditional engine start, and why it used to be so damaging. In an older vehicle, when you turn the key, you are asking a small electric motor, the starter, to physically shove a massive, cold, dormant lump of metal into motion. It takes a tremendous amount of amperage from the battery. The starter gear jams into the flywheel with significant force. And crucially, the oil inside the engine has drained down into the pan. For those first few rotations, metal components are rubbing against other metal components with minimal lubrication until the oil pump spins fast enough to build pressure. That is where 90% of engine wear occurs, the cold start. Auto start-stop is fundamentally different because it almost never performs a cold start. The system is designed only to operate when the engine is already up to operating temperature. This changes the physics entirely. When your engine stops at a red light, it is hot. Crucially, modern synthetic oils are designed with high film strength retention. Even though the oil pump stops, a microscopic layer of lubricant remains clinging to the crankshaft bearings and cylinder walls for several minutes. When the system restarts the engine 10 seconds later, it is not metal on metal. It is lubricated surfaces re-engaging on top of an existing oil film. The wear during a hot restart is practically negligible compared to the morning cold crank. But what about the starter motor itself? Surely, using it 50 times a day instead of twice must destroy it. This is where the biggest engineering changes have occurred. The starter motor in a car equipped with auto start-stop is not a standard part. It is a heavy-duty, reinforced component designed specifically for high cycle duty. A traditional starter might be rated for roughly 50,000 start cycles over its lifespan. A start-stop starter is typically rated for upwards of 250,000 to 300,000 cycles. How do they achieve this durability? They use different internal brush materials that resist wear better. They use stronger planetary gears to handle the torque spikes. Furthermore, the engagement mechanism is different. In some advanced systems, the starter gear remains meshed with the flywheel as the engine spins down, ready for an instant restart, rather than having to violently crash back into gear every time. Then there is the battery. A standard lead-acid battery would be destroyed in months by the constant deep discharging and rapid recharging required by this system. Cars with auto start-stop almost exclusively use AGM, absorbed glass mat, or EFB, enhanced flooded battery, technology. These batteries have entirely different internal architecture. The electrolyte is held in glass mats suspended between the plates, allowing for much tighter packing, lower internal resistance, and greater resilience to deep cycling. They are designed to handle the electrical load of running your AC fans, radio, and lights while the alternator is off, and still have enough punch to instantly restart the engine. Finally, there is the brain of the operation. The computer doesn't just blindly shut the car off when speed hits zero. It monitors dozens of parameters. Is the engine warm enough? Is the outside temperature too cold or too hot, requiring the AC compressor to run constantly? Is the battery charge level above a critical threshold, usually around 75%? Is the driver applying enough brake pressure to indicate a full stop versus a momentary yield? Is the steering wheel turned sharply, indicating a tricky maneuver where sudden power loss would be dangerous? If any single one of these parameters is not met, the engine stays running. It is a highly calculated pause, designed to prioritize vehicle health and passenger comfort over fuel saving. Now, let's see how this technology manages different real-world environments. We will simulate 3 common driving scenarios to understand where the system shines and where it struggles. Scenario 1. The suburban break-even light. You are driving in the suburbs on a mild afternoon. You approach a major intersection just as the light turns red. You know this is a long cycle, perhaps a 90-second wait. You come to a complete stop, foot firmly on the brake. The computer runs its checklist in milliseconds: engine hot, battery full, cabin comfortable. It cuts fuel and spark. The engine goes silent. This is the ideal scenario for auto start-stop. The biggest misconception is that starting the car uses more fuel than idling. Engineering studies have established a break-even point for most modern engines. It is typically around 7 seconds. If you are stopped for longer than 7 seconds, it is more fuel efficient to shut the engine off and restart it than to let it idle. At a 90-second stoplight, you are saving significant fuel. An idling 2.0-liter engine burns roughly 0.3 to 0.5 gallons per hour. Over the lifetime of a car, sitting at lights like this accounts for a massive amount of wasted energy. By cutting the engine here, you are saving fuel, reducing emissions in a dense area, and because it's a hot restart, you are incurring virtually zero mechanical penalty. Scenario 2. The freeway stop-and-go nightmare. Now, let's move to the environment that makes people hate this feature. Rush hour freeway traffic. You drive 20 feet, then stop for 3 seconds. Drive another 10 feet, stop for 5 seconds. In early versions of auto start-stop, this was miserable. The engine would shutter off, then immediately shutter back on, over and over again. This is where the thermal limits of the starter motor come into play. Even reinforced starters generate heat when they work. In this scenario, a modern system will eventually disable auto start-stop temporarily. The computer monitors the temperature of the starter solenoid. If it detects rapid cycling that could cause overheating, it will keep the engine running until the components cool down. It prioritizes protecting the hardware over saving those few drops of fuel in creeping traffic. Modern systems have also refined the restart to be much smoother, often firing specific cylinders first to minimize the shudder that annoys drivers. Scenario 3. The drive-through inch forward. This is perhaps the most frustrating scenario for drivers. You are in a coffee shop drive-through line. You stop at the speaker to order. The engine turns off. You finish ordering and lift your foot off the brake to creep forward 3 feet. The engine restarts. You stop again. The engine turns off. You are stopped for maybe 4 seconds at a time, below that 7-second break-even point. Here, the system can feel counterproductive. However, advanced implementations are getting smarter. Some vehicles use radar sensors in the front bumper. If the car sees the vehicle immediately in front of you moving away, it might preemptively restart the engine before your foot even leaves the brake, making the transition seamless. Others monitor the rate at which you release the brake pedal. A slow release signals inching forward, and the engine may restart gently. A sudden release signals green light, and it restarts aggressively. While this scenario is still the least refined, the engineering goal is to ensure that even if it's annoying, it is never damaging the vehicle. So, what is the takeaway for the daily driver? The auto start-stop system is not a conspiracy to break your car. It is a complex, heavily engineered response to the need for greater efficiency and lower emissions in urban environments. The hardware, the starter, the battery, the bearings, has been upgraded to handle the task. The software is designed with dozens of safety checks to prevent damage. If you absolutely hate the sensation, go ahead and press the disable button. It's your car. But do so knowing that you are disabling it for comfort, not to save your engine. The only times you should genuinely consider manually disabling it for mechanical reasons are in extreme outliers. If you are doing heavy towing and stop at the top of a steep hill, keeping the engine running to circulate coolant might be wise. If you are off-roading in a precarious situation where instant throttle response is critical, shut it off. But for 99% of your daily driving, the commute, the grocery run, the school pickup, the system is working exactly as designed. It's saving a little bit of fuel at every stop, which adds up to massive savings across millions of vehicles globally. And thanks to the hidden engineering we've explored today, it's doing it without sacrificing the longevity of your machine. Thanks for watching. If you want to know how the latest mild hybrid systems make start-stop completely imperceptible, let us know in the comments, and we'll cover that in a future video. Drive smart, and we'll see you next time.